divided into main subparts. The first part is introduction. For a long time, in order to ensure the network security of the vehicle bus network, automobile manufacturers have unified the use of lead, CAN, and flex-rate buses to independently build the vehicle bus network. However, the development of vehicle bus networks faces many challenges: the network security, data management, and the network technology of the vehicle bus network traditionally lack security guidance and have strong arbitrariness and hardware dependence. In July 2015, several security experts, neither C and BERT hacked into the cars. So many people will pay attention on the security of cars. The second part is flex-rate protocol. In this picture, we can see the frame of flex-rate data frame is divided into three parts: the start segment, the payload segment, and the end segment. We can see the payload length indicates the length of the payload of frame, and the header CRC is used to check the redundancy of the initial segment and errors in transmission. The payload segment contains valid data to be transmitted. The trigger segment is composed of 3 bytes CRC check node. And the second part is the AS algorithm. In this paper, the picture we can see is the process of AS encryption and decryption. Each step of the decryption algorithm corresponds to the reverse operation of the encryption algorithm. The sequence of all encryption and decryption operations is precisely the opposite. The joint process of each step of the encryption algorithm, the decryption algorithm ensures the correctness of the algorithm. The key for each round of encryption and decryption is obtained from the safe key through a key expansion algorithm.
We can cancel all the video.
This paper proposed the modified AS algorithm.
Session 3 and 4. Sorry about that.
In order to improve the encryption efficiency, and the column mixing change is to multiply the metric after the previous transformation with a constant metric, so that each element in the metric is the weighted sum of all the elements in the original column of the elements. Among them, the multiplication is performed on the finite field GF field, and the modulo polynomial GX is required in the AES algorithm. The metric can be expressed by expression 1. And the column mix of the ith column is in the state metric can be expressed by the fraction 2. The inverse mix the transformation is expressed by metric multiplication in fraction 2. And in this paper, in order to increase the speed of message encryption and reduce the number of multiplication, the above mentioned metric is replaced with an optimize the metric multiplication. Let G be a generator in the finite field. Then M, N, O, P are the orders of A, B, C, D, respectively. Then can be conjectured as the following expression. The expressions file can be obtained through the calculations of the conventional metric, and since any element in GF can be obtained by the power from GK of the generator G, all polynomials can be obtained in the form of the power of G. The metric M that satisfies the constraints is F. The fourth part is the experimental results. In order to verify the effectiveness of the modified max-column AES encryption we proposed in this paper, the paper carried out 1,000 encryption and decryption experiments on 4 groups of flexibly message data. Feature 6 is a time compression line chart obtained in MATLAB for encrypted flexibly message data, and B shows the situation during decryption. Compared with the original AES algorithm, the encryption speed of the modified AES algorithm is increased by about 26%, and the decryption speed is increased by 30%. It can be seen that the modified AES algorithm proposed in this paper reduces the time delay when encrypting and decrypting flexibly messages. In order to further verify the effectiveness of the modified AES algorithm proposed in this paper on the vehicle flexibly bus, this paper uses the CAPO languages to write the modified AES algorithm program. It conducts simulation verification through CANOE vehicle bus network development equipment, and in the feature we can see new ECU TX and the new ECU RX are the sender and the receiver nodes of the flexibly bus, respectively. In the right feature, we can see the message data, and there is no error. In this paper, 2 flexibly hardware development flows are used in flexibly transmitter and the receiver nodes, and VN8970 is used as the flexibly communication interface to realize the communication between CANOE and 2 flexibly nodes. The structure of the hardware experiment environment is shown in the figure, and the actual hardware simulation environment is shown in the figure. In the last is the conclusion part. Aiming at the network security problem is of flexibly bus. This paper innovatively proposes and modified the mixed-column AES algorithm encryption scheme based on the analysis of the software and hardware experimental simulation analysis results based on the CANOE and flexibly development version. The modified AES encryption speed is about 26% higher than the traditional AES encryption algorithm, encryption speed is increases by 30%. This scheme can effectively encrypt and improve the time-consuming problem of encryption and decryption of the original AES algorithm. The further improves the encryption and decryption speed and efficiency. At the same time, it makes up for the key problems of resource waste and time delay when encrypting and decrypting flexible message data, and lays a solid foundation for the network security technology of the onboard flexible bus network. Future work will contain about two parts. The first one is considering the robust of environment, and the second part is how to improve the algorithm performance.
Hello everyone. The title of my thesis is Design and Optimization of Big Data Connection Algorithm.
Hold on. Dr. Fan, I think
Yes.
that's the video presentation for the first paper. Look, we're gonna have to cancel all the pre-recorded videos and only allow that the live presenters to speak. We are having technical issues of the other sessions.
Okay, no problem.
Yeah.
So
why don't you go possibly our next presenter who is in the session, and then after we finish, we'll allow that session chairs, maybe our session 2 to start the presentations in the sessions scheduled over there.
okay.
We're going to use the same session here.
Okay, no problem.
All right, thank you.
No problem. So let's go to the third paper in this session, which is an urban sound classification using deep learning. Welcome the speaker.
Yeah, hello, sir. Am I audible?
Yes. Please go ahead.
Yeah, should I share my screen?
Yes, please. Thank you.
So hello one and all, and the conference shares. And topic of my paper is urban sound classification using deep learning based intelligence system. The authors are Ruturaj Ghodke, myself, Priyanka Gaikwad, Rutuja Hulsare, Prajan Shukla, and Dr. S.V. Limka. So just like sight or vision, sound also plays a vital role in our daily life. Even without sight, sound helps us understand what is going on around us and hence giving crucial information. So just like our eyesight or any camera, security cameras, when they look around, they what do? They identify the object that is around them, and then they gain the information from them. But what's the limitation? Is that they can only see what is limited by the range. But with sound, even though even without eyesight, we can if we can identify the source of that sound, we can immediately get the information like what is going on around us. So just like eyesight, sound is also important when we are analyzing the environment around us. Today, majority of the intelligence systems rely on vision or other factors for the applications, and sometimes the importance of sound here is neglected. So when we see today various applications, so we use computer vision, and most of these use visual representations for their analysis. The ability to classify and predict environmental sounds paves a way for a broader set of applications and also enhances existing ones. So let's just say, take the example of surveillance cameras again. if we can inculcate the ability to predict and classify environmental sounds with their ability to see or use the site, we can combine these two applications for a bigger role. So using deep learning models like CNN, we can predict and classify environmental sounds and use it for various applications effectively. We're going to see it how. The purpose of environmental sound recognition and classification has received much attention in recent years, as this research has already is just recently being done. Analysis of environmental sound is difficult because of its unstructured nature. That's correct, because let's take example of music. So music can be in a structured way. It can go in loops. It can have a basic structure. Like we can classify different instruments based on the frequency pattern and their range. But environmental sound, there's no particular structure for it. So there's no structure for traffic sounds. There's no particular structure for wind sounds or anything, right? There are multiple applications already proposed in a big variety of industries, including surveillance, audio scene recognition for robot navigation, acoustic monitoring of natural and artificial environment. And therefore, we can contribute more by coming up with more innovative and effective applications in this digitally transformed society. We referred quite a few papers here. The first paper states that they used background sounds from a video or sound clip with foreground human speech to be identified using VGG network, which is a CNN model. They also used a custom-made data set called YBSS 200, which got them a maximum accuracy of 80.2%. The VGG model is known to have very good accuracy rate, but the new data set they used had many noisy data, which hindered accuracy. Similarly, the second papers they also used convolutional neural networks with dilated filters and with a leaky railway activation function. The data sets they used were Urban Sound 8K, ESC50, and CIC ESC. The model proved to be 2% more accurate than CNNs, but at a higher cost of higher complexity power and greater storage. Similarly, the third also used capsule neural networks. They also used different data sets as mentioned. They also achieved a result of 78%. Similarly, other two papers. The first one used multi-scale time frequency convolutional recurrent neural network. This is a modified model adopted to improve sound event detection performance and reduce the neural network parameter counts while saving computational power. Also, the last paper we referred was where they used CNN transformer, which performs similar to a CRNN, and an optimal threshold optimization method is also used. The drawback is that the advantage is that this method works on weakly labeled data sets and where there are only audio tags for each audio clip. Here comes the problem statement of our paper. Analysis of environmental sound is difficult because of its unstructured nature. However, we find the presence of strong spectrotemporal patterns in them, which makes classification possible. With the increasing demand of applications requiring identification of urban sounds, we use effective deep learning models to analyze and classify environmental sounds. So this is how we are classifying environmental sounds. First, we use a deep learning model known as convolutional neural network for our classification. For our data set, we use an openly available data set known as Urban Sound 8K. It is a public data set containing over 8,000 environmental sounds of 10 different classes. So there are 8,000 sounds of 10 different sources. The proposed architecture split into two phases, that is the pre-processing phase and then the CNN phases. Here is our system architecture, which were given in brief in a diagrammatic model. We can see at the below that it's split into two parts, that is the pre-processing part and the CNN part. Each of these parts is being further detailed, explained in detail. So let's go to the first part. For the input for the CNN model, we use Urban Sound 8K. So Urban Sound 8K contains 8,732 labeled audio clips, which contains environmental sounds. We can see the types of classes are mentioned here, like car horn, children playing, dog barking, drilling. These are all environmental sounds that we get to hear from our everyday, environment and nature. Also street music and siren, jackhammer. These are on the type dot wave format. Now the pre-processing phase. What we do, we don't directly analyze or we don't directly put the audio file to the CNN. what we do is we first convert these audio files into a spectrogram. Now, what is a spectrogram? A spectrogram is a visual way of representing features of sound, mainly signal strength or loudness over time at various frequencies. So basically, a spectrogram is an image. It is a visual representation of that sound. What is that image? That image is a graph, is a graph basically of frequency, time, and power. So we can see in short that audio file, which is .wav, MP3, or OGG, it will be converted into JPG format. How basically a spectrogram looks is being given here. So let's take an example. The left-hand side of the images are not spectrograms, but they are just normal waveforms that we plotted in Python. And basically the waveforms is just a frequency versus time. So frequency versus time graph is just a normal waveform. But when that audio file is converted into a spectrogram, you can see the difference where it's the frequency is also given, the time is also mentioned, and also the power, which is in decibels. So we can see as the power increases, the colors become lighter. The colors become lighter. So here are two audio samples. After that, after these images are converted to spectrograms, we feed them to the neural network. Now we have four layers of convolution and pooling layers in our neural network. So first, what happens? We know that the system or computer reads an image in a form of matrix, right? So the matrix size is based on the size of the image in how many pixels are there in each rows and columns, and the value in each of the cells of the matrix represents the value of the color at that pixel, right? So this matrix is fed to the CNN. And one of the first sub-layers it encounters is the convolution layer. So convolution layer, what it does is it basically extracts features from that image. How does it extract features? The image is cross multiplied with a filter. Now the filter is a part of image, a part of a sample image. Like it may contain a boundary, edges, or corners. It depends on what layer you are. So as the layers are increased, the features of filters get more complex. So initially we have corners or edges, and then we can combine them into more complex features, right? So what happens here? Each part of the image is multiplied with a filter, and if it matches, then it will give a positive result. If it does not matches, it will give 0. So that's how features are extracted. Second, to add non-linearity to our data, as we want to classify, we have to add an activation function. We use ReLU function. We particularly use ReLU because it eliminates all negative values, so it may help in our computations. We can see that all values below 0 will stay as 0, and all values above 0, it will stay what they are, as shown in the graph. After that comes the pooling layer. What pooling layer does, it trims down the number of parameters when the images are too large. So this is also known as subsampling or downsampling. It reduces the dimensionality of each feature map, but retains the important information. Hence, this decreases the computational power used for processing the data. So we can see if we use max pooling, then only the maximum values are stored in each cell, whilst also reducing the dimensionality of the matrix. So these three sub layers are repeated 4 times. We use 4 layers because that's what gave us a maximum accuracy while we were training a hyperparameters, tweaking a hyperparameters. Then after all 4 layers, we finally come to the fully connected layer. The fully connected layer flattens the matrix. After flattening the matrix, we see a flattened matrix representation below. We use a softmax function. Now, why we use softmax function? Because we want to classify our sounds into 10 classes. The softmax function basically assigns weights, a probability to which the sound file belongs to, and whichever class has the highest probability, that is the class that the sound belonged to in the first place. Finally, we get to our results. So for training, we train the model on 4 layers of convolution pooling layers, as I said. ReLU activation function is used after ReLU convolution layer. Finally, softmax function predicts the probability of the sound in 10 classes. Our model achieved a training accuracy of 98.73 and a testing accuracy of 89.38%. The model is trained on 150 epochs with a batch size of 64. The model is also evaluated using 10-fold cross-validation. What we found that was when we add dropout of 0.1, that is 10%, the model gave us an approximate increase, 2% increase in our testing accuracy, that is from 87.13 to 89.38. Hence, whatever a small part of overfitting we had in a model, the dropout did regularize the model and it bumped up our accuracy. Any further increase in dropout value, the accuracy decreases. So this is the confusion matrix which we plotted after our initial testing. So the labels and the x and y values are nothing but the classes which are encoded in an integer format. So the diagonal values, to be put it simply, the diagonal values are the values which are correctly labeled. So we can see the diagonal values that are higher in number are the values that are correctly labeled. The other values that are light colored in number are the incorrectly labeled values. So we can see that our model predicts the input values with a higher accuracy. Here is the output. As you can see, the spectrograms that we converted, the model predicts the labels and they are written above their spectrogram. So we can see the first image, the model predicted the image as jackhammer sound. The other, the children playing. We can also see a dog bark spectrogram. The model predicts the sound as dog bark and also air conditioner sound. What applications can we use? As I said, we can use it in security and surveillance. So we can also identify cameras. We can also identify sounds, and we can act upon this. We can use it for assisting as an assisting tool for the disabled people with hearing problems. So we can use this system in an application or something, and disabled people can use it for their needs. Scientists can use it to further study environmental sounds. Can be also used in home automation systems for home security systems, for alarms, and also used in audio and recognition for robot navigation. So not only robots can use now the power of vision, but also can use the power of analyzing sounds. Advantages of this system is that good accuracy for predicting sound due to usage of CNN. Why we use CNN? Because we all know that CNN, convolutional neural network, works best with image data. So why not harvest this power of it using the predictive image data with sound? So that's why we converted sounds into images basically, and then use CNN to predict them. Time required for classification and identification is comparatively less. Human effort is reduced due to automation, obviously. Cost of hiring domain experts is reduced due to automation of data. Data sets of larger sizes available, which helps in further improving accuracy. And noisy data in the input is pre-processed before feeding it to the core system. Here are some of the limitations that we found out: that the system may require initial time for machine learning model due to large data set, because the process of converting the sounds or the audio clips into spectrograms can take some time. So as the data set grows, the initial conversion from audio set to the audio to the program may take time. It's very difficult to find clean and noiseless data sets for initial learning. And accuracy for multi-class classification is comparatively less efficient. Also, noisy data will lead to incorrect predictions on the output side. Finally, what we conclude is that our system identifies and classifies the particular environmental sounds fed at the input. The system uses urban sound 8K as an input data set, and after converting all the sound clips to the spectrograms, they are classified and predicted by using CNN. What can be the future scope of this project? If we obtain a larger data set with more classes, in using a machine that can handle higher complexity loads, we can accept a more broader set of sounds to be classified with an even better accuracy. With an automated audio cleaning system integrated. Now, what if we can't find clean audios everywhere? If we integrate an audio cleaning system, we can also make use of the noisy data that is available. The noisy data will get cleaned, and then we can use it for our analysis, like just like a data set. Also, the system, if you use the system as a backend of an application, users can make use of this predictive ability by any device from their client side. These are some of the references that we use for our study. And finally, I said thank you. That's the end of my presentation.
Thank you very much. Before Dr. Fan and also questions, let me make an announcement. Since we had our technical issues, we created 2 sessions for session 1 and 2. So please, the chair of session 1 and session 2, if you're here, please join the session I posted in the chat. And also the presenters, please join those newly created sessions over there. Again, they are in the chat. So if you're not familiar with the some of the window, and you will see a chat message, and from where you can get the session links.
Okay. So thank you. Any questions for the presentation?
I have a quick question. Did you get a chance for the author? Did you get a chance to compare with other methods?
Yeah, so we kind of studied the LSTM model, that is a long short-term memory model. We tried to study that in some other papers, but we found out that they had some limitations, like they used a bigger data set, but they still got hindered in their accuracy. So what our main motive was to make use of as much as high accuracy as we can, whilst also use as much less running time in our system. So we found out that the CNN model used a lot lesser running time with higher accuracy. So that's why we use this.
In terms of time, I don't recall you present the computational time here. Did you get a chance to look at the time it costs to train and then possibly test the model?
Obviously the time depends on how big of a data set is. So as we use like around 8,000 input samples here, the training time took along 5 minutes of training time. But when we use it for predictions, for testing, it's just a matter of seconds, like 3 to 4 seconds, when the model predicts correct data at the end.
Oh, training time is very short.
Yeah, so we tweak some hyperparameters. We tried to test it on how different layers, like how many layers we should use, how many input what do we say, like filters and all. We tried to test it on different hyperparameters, and 5 to 8 minutes was the average training time. Also depends on the system. Like we used Kaggle notebooks, so they had these GPUs already installed in them. So I think that's what helped us to get such a short amount of training time.
All right, thank you.
Yeah, thank you, sir.
Okay, then we go to the next presentation. That is emotion recognition using natural language processing and BERT. And welcome the author, Harper Itkata.
Yes, thank you.
Okay.
Please could I share my screen?
Yes, please.
Okay, so hello everyone. The title of our presentation over here is Intelligent Emotion Recognition Using Natural Language Processing and BERT, authored by Suresh V. Limkar, Apurva Itkarkar, myself, Yash Kasad, and Nikhil Mandal. So coming to our topic, coming to the introduction. So as we all know, emotion is one of the important aspects of our lives that influences all our day-to-day activities, social behavior, friendship, family, and many others. So being able to recognize these emotions can help us in various domains such as psychology, human-computer interaction, marketing, e-learning, and many more. So emotion recognition in text is an important aspect of natural language processing. So herein, we have done a comparative study on different approaches, that is a traditional machine learning approach, neural network approach, and bidirectional encoder representation from transformers, that is our main model, the BERT model, to evaluate which approach gives us the maximum accuracy. And the output that will be generated will be emotions identified from text, classified into 5 labels, that is joy, sadness, fear, anger, and a neutral one. Coming to the objectives, so it can help a particular enterprise organization to learn about people's reactions to certain events. This will help to get better feedback as well as to devise a better business model for marketing minds. It can help us in psychology, in education. The analysis of emotions on a large scale is important because text is also one of the most common ways of communication with the growth of social media and social networking. Coming to the literature survey, the papers that we studied, the first one, that is recognizing emotions in text using ensemble of classifiers. So in this paper, the authors utilized NLP techniques, including POS tagging and parsing, to analyze the structure of a sentence. The emotion words were recognized using the WordNet effect, and what was seen that it was a non-robust classification technique, and it affected the system performance. So the performance of the system was not so up to the mark. Coming to the next one, that is exploring fine-grained emotion detection in tweets. The authors in this paper proposed 2 learning-based approaches, but they worked on quite a large number of emotions, that is 28. The experiments demonstrated that the SVM and Bayesian networks consistently provided a good performance. Next, coming to the next paper, that is emotion and sentiment analysis from Twitter text. The authors in this paper collected tweets and replies on specific topics and created a data set with text of the users, the emotions, the sentiment information, etc. So they used this data set to detect sentiment and emotion from tweets and its replies, and measured the influence scores of the users based on various user-based and tweet-based parameters. So even this model had quite a low performance. Then coming to the next paper, that is emotion recognition from text stories using an emotion embedding model. So in this paper, they proposed an emotion embedding model that is created by developing a word embedding layer. It doesn't take into account the semantics of the text, and also the emotion of joy was predicted with a higher accuracy as opposed to the emotion anger. So what we have seen from these literature surveys, coming to the summary, that is by evaluating these present methodologies, it is seen that the previously built models, the accuracy was, that is the system performance was quite low, and that they had, because there was a use of unbalanced data sets, and also in some scenarios, the model failed to predict implicit emotions from text, that is wherein the emotion word has not been specified in the text itself. So in those scenarios, the model at times failed to predict. Coming to the data set that we have used. So the data set was combined from 3 data sets, that is daily dialogue, ICDSIS, and emotion stimulus data set, to create a balanced data set with 5 labels, that is joy, sad, anger, fear, and neutral. The text mainly consists of short messages and dialogue utterances. And there's one of the, there's a example from the data set, that is what will be the text and the emotion related to it. Okay, now coming to the proposed system architecture. So we have tested on 3 models, that is traditional machine learning, a neural network, and a BERT-based approach, to check which of our models gives us the maximum accuracy with the correct results. And for this, first providing our data set as the text input. The pre-processing is a very important aspect when it comes to natural language processing. So that is when we work with text. So we, for certain of these approaches, stop word removal, stemming, lemmatization, BERT pre-processing, we will come to it. Then POS tagging and removal of extra white spaces has been done. Coming to our approaches, the first one, that is our traditional machine learning approach. So herein, what we have done is we have vectorized our text using the TF-IDF, that is the term frequency inverse dense frequency technique. So what is done in this is that it quantifies a word in the sentence, that is, it signifies the importance of the word in the corpus. Then we will use the classifiers and classify these sentences. We will use different classifiers and classify these sentences into our 5 emotion categories. So the classifiers used have been mentioned over here, that is naive bias, logistic regression, random forest, and SVM. So what outputs we have received from this approach is naive bias gave us an accuracy of about 67.02%. Random forest, an accuracy of about 63.72%, logistic regression, an accuracy of 69.35%, and SVM, an accuracy of 72.71%. Next, coming to our second approach, that is the neural network one. So here, what we have done is we will be importing pre-trained word to vector file. So word to vec from file, sorry. So here, what is done is we have used a 300-dimensional word vector that has been pre-trained on Wikipedia articles, and we have created an embedding matrix. We have then mapped each word in our corpus to the existing word vector. So coming to the model pipeline. So the first level creates embedding of words using vocabulary with a certain dimension and a given size of the embeddings. We then use a 1D convolutional neural network to extract features from our data in case of CNN. That is, pattern is detected. So by varying the size of kernels and concatenating the outputs, we can detect patterns of multiple sizes. Then coming to LSTM. So the LSTM layer will receive word embeddings for each token in the text as the inputs. The intuition in this is that its output tokens will store information not only of the initial token, but also any previous tokens. So basically the LSTM layer is generating a new encoding for the original input. The output level has a number of neurons equal to the classes of the problem and a softmax activation function. So the output of this approach, the accuracy is that, and word to vector gave us an accuracy of about 75.66%, and LSTM plus word to vector gave us an accuracy of 73.56%. Now, coming finally to our main model, the BERT model. So the use of bidirectional encoder representation from transformers, the BERT model, we have used this to gain it has advantages as it gives us a context of words from both left to right and right to left simultaneously. And the text needed to be processed in a specific way for use with BERT. So for that, we have accomplished that by setting the PPROC model to BERT, pre-process mode. Then the BERT model, I'll be explaining it next. We obtained an accuracy of about 91.72% in our model. So coming to the overview of our BERT model. So the BERT model, it will be using 2 inputs, one from words tokens and one from the segment layer. So these get added, summed over to a third embedding layer, that is the positional embedding, followed by a dropout and a layer of normalization. Then starts the multi-headed self-attention layers. Each set of these have 9 steps, and there are 12 such layers. Now, following these 12 layers are 2 outputs, one for NSP, that is next sentence prediction, and one for MLM, that is the masked language modeling. Then to compile the model, we have used the binary cross entropy function, binary cross entropy loss function, as the loss computed for every output vector component is not affected by the other component values. Therefore, it can be used for it is advantageous for used with multi-label classification, and also the Adam optimizer, as the optimization for gradient descent efficient, it is quite efficient. Coming to the results obtained, as we can see that some input was provided to the model. That is, for example, this movie was horrible, the plot was really boring, and the acting was okay. So the model predicted that the emotion is sad, that the user is not very happy with the movie. Now, the second sentence is that we got a new puppy. So in this sentence, the emotion as such has not been explicitly specified that what is the user feeling, but the model did predict that the emotion attached to it was joy. Then next, coming to the third one, that what a beautiful movie. So the model did predict that the user is feeling joy in this case. So coming to the case study results of all our models. So the CNN plus Word2 vector so these are the outputs of all our models, that is CNN to Word2 vector, LSTM plus Word2 vector, and the traditional machine learning approaches. So these did classify our emotion into the proper emotion categories, but what was also seen is that we only we didn't have a multi-label classification as such in these techniques, and they didn't classify the implicit sentences so well, and even the time required was quite more as compared to our BERT model, that the BERT model could again, yes, give us a better accuracy and a better performance. Coming to the conclusion, so we have seen that the BERT-based model gave us a more accuracy as compared to other models, that is of about 91.72%. So our model was able to classify emotions from implicit text, that is where the emotion is not explicitly specified. As coming to the future scope, the model can be trained on different languages on a greater data and on a bigger data set, and can also be trained to include more emotion classes into it. These are some of the references that we have used. And that is the end of my presentation. Thank you.